Good evening, everyone. My audio is clear. Okay. So, in this lecture, we have to study the topic optical communication. So, let me select the color of the pencil, the pen, and this one green one. Okay. So, the intro portion of the optical communication. So, let's start. Optical, optical detectors. Okay. Detector. Okay. Okay. So, okay. Detector are the device. Mm, are the device. Okay. Device used at the receiver end. Okay, used at the receiver end. Okay, receiver end and receiver end of the optical fiber. Okay, optical fibers. Okay, in a communication system. The main job of this optical fiber is that actually it converts the optical power into the electrical signal. Okay, and this electrical signal then this electrical signal can then be amplified, processed, demodulated, and intercepted. Okay, then that electrical signal that we get from the optical uh, through the conversion, the optical this electrical signal can be amplified. This electrical signal then amplified, amplified, processed, and demodulated. Okay, and demodulate, and because the detector is when the optical signal is and because the detector is where the weak optical signal is finally captured. Overall system performance is determined at this stage. Okay, a good detector reduce the number of repeater required. So actually the good detector simply reduce the number of repeater required for saving the cost and the linkage. Okay, why detectors are important? So that attenuation, dispersion, noise, and accumulate along the fiber. So why, the question is why we use detector? Okay, so why we use detector? The question is why we use detector. Okay, so detector is used because attenuation, dispersion, and the noise accumulated along the fiber, the detector must accurately extract the signal from the impaired light. Okay, thus improving the detector performance and improve the entire communication system. So is the photo detector is important? So why is photo detector is important? The photo detector. Okay, attenuation, dispersion, and the noise accumulated on the fiber. Okay, along the fiber. So the detector must accurately extract the signal from the impaired light, and thus improving the detector performance and improve the entire communication system. Performance and compatibility requirement. Okay, high sensitivity at the optical wavelength. The first generation optical system is 02 and 0.8 to 0.9. This one. Okay, we can see high sensitivity. The first generation system has wavelength has 0.8 to 0.9 something, and the second generation system moved to 1.1 to this one. Okay, the fiber attenuation is lower and chromatic dispersion increases. So the dispersion reduces. Okay, therefore the detector material must provide a good sensitivity at the wavelength at room temperature 300 Kelvin. Okay, and after that high fidelity. So high fidelity high fidelity for analog link, detector must produce an output electric signal is exactly proportional to the input signal. For the high fidelity, the output linear. This means that the input optical signal. So when the output electrical signal is exactly proportional to the input one. Okay, that's this was the linear property. Okay, after that the large electrical response. After a large electrical response means high quantum efficiency. High quantum efficiency means that a good detector should produce strong electrical output for the minimal optical power. Okay, good detector produce strong electrical output for the to support a high data rate advanced fiber system many tens of gigahertz. Okay, future WDM system has a terahertz range. Okay, therefore detector must be extremely fast and minimal carrier transmit. Okay, minimum noise reduced introduced by the detector. Minimum noise introduced by the detector. The noise should reduce the dark current leakage current. Okay, noise should reduce the dark current leakage current thermal noise and excess noise and internal gains. Okay, avalanche process. Okay, and low noise is essential to achieve the high sensitivity. So low noise is required to achieve the high sensitivity. Stable performance with the temperature, and we have a uh, stable performance stable performance stable performance with the temperature. So photodiodes, actually the photo sensitivity and noise vary with temperature. Sensitivity and noise vary with the temperature. Okay, ideally the detector should remain stable under the ambient variation, but the practical receiver use. Okay, thermal compensator or feedback circuit. Okay, small size, so it's needed for the efficient coupling to any tiny codes. Okay, compact packing with the amplifier and the electronics, better bandwidth due to reduced capacitance. Okay, low bias voltage, so ideally the detector should not require excessive bias voltage for current. Okay, reduce power consumption, reduce noise, so ideal detector should operate at a low bias. This means it reduce the power consumption, reduce the noise, and the improve long term reliability. High reliability, so detector must work continuously for the year. Okay, at room temperature but duration. Low cost, economic consideration often of the prime importance in any large scale communication application. Okay, so these are the 10 performance and compatibility requirement of an optical detector. Okay, so detector must satisfy these 10 very strict requirement. Okay, high sensitivity, so high sensitivity at the operating wavelength, high fidelity. Okay, in which input power is directly proportional to linear. Large electrical response at the receiver, slower response time, minimum noise, stability with characteristics, small size, low bias voltage, high reliability, low cost. Okay, so these are the 10 things. So and in short we have to explain optical detector convert the optical power to electrical power. So optical power to electrical power in a fiber communication system. Okay, overall system performance is strongly influenced by the detector characteristic. Okay, and the modern system mostly use semiconductor photored, and the modern system mostly use semiconductor photodiode due to the high sensitivity, speed, and reliability. The key performance parameters include quantum efficiency, responsivity, speed, noise, temperature, stability, compatibility with the fiber wavelength. Okay, and we move forward for the device type. Okay, so move forward for the device types. Okay, so let's see device types. Okay, device type. So optical radiation in a fiber optical communication is mainly is near. So as we know that the optical radiation in a fiber optical communication is nearly infrared, infrared region. Okay, region actually it from the 0.8 to 1.6 uh, micro ampere. To detect this photon, we use a photoemission process to convert photon into electron. So to detect these photon, we use emission. We use photoemission emission photoemission process that convert the photon to electron. Okay, electron. The two main detection mechanism. First one is external photo mechanism. So there is two mechanism through the external one, external photoemission. Okay, external photoemission and external photoemission in which example is multiplexer tube. Okay, and second is internal photoemission. Internal photoemission. Okay, preferred. So let's see, and then after is intensity extensive photo detection. Okay, then material choice. Okay, let's cover in speed. So device type. So in device type we see, let's discuss. So for the external photo emission, external photo emission. So the example is photo multiplexer tube, multiplier tube, vacuum photo layer. So characteristic of the external photo emission is the electron are emitted from the surface of the metal where photon strike. Okay, so they have a good sensitivity and high gain and fast response, but they are not suitable for the optical fiber communication because it is bulky, because they are not suitable because they are bulky, require very high operating power, poor compatibility with the compact fiber, so therefore they are not used in the optical fiber communication. So external photo emission. And second one is that internal photo emission. Okay, so this is the mechanism used by semiconductor photodiode. These are the semiconductor photodiodes, the primary detector in a today's optical fiber. They are preferred because they are small. Okay, they are small, they are low cost and the high sensitivity and the high speed and compatible for the compatible with the fiber wavelength and low operating voltage. Okay, the common semiconductor metal are silicon. Okay, silicon germanium and the uh, 3v alloys. Okay, these metals satisfy the detector requirement for the sensitivity, speed and noise and cause. So the difference between intrinsic versus extrinsic photo detection. So in the intrinsic semiconductor photon electron. So intrinsic semiconductor photon electron excite electron from the valence band and the conduction band. Okay, direct band to band absorption, fast and efficient. Almost all fiber optics detect use intrinsic. So the intrinsic versus extrinsic. So photo detection, detection. The two types. Okay, so first of all, in the intrinsic one is that photon electroexcited. So valence band. Photon energy excite electron from the valence band to conduction band. Valence band to conduction band. Okay, and then after and band to band absorption, fast, efficient. Almost all fiber use extrinsic photoconduction, intrinsic detection. Extrinsic semiconductor contain impurities, dopant level in the band gap. Okay, and the photon excite an electron from the impurity level to photon excite, in which the photon excited from excited from the excited from the impurity level to conduction band. Okay, okay, conduction band usually slower, not preferred for the high speed, and one is lower, not preferred for the high speed. Therefore, the intrinsic absorption is used for the all modern photo diode for the optical fiber communication. The material choice is the silicon photodiodes. Okay, silicon. This was the excellent for the 0.8 to 0.9 micron and used for the first generation fiber. Okay, high sensitivity, high speed, low dark current, and high reliability. Silicon has an indirect band gap of 1.4 electron volt. Then after germanium and the 3,5 photodiode. Because the second generation system use a longer wavelength, okay, material with a smaller band gap are needed. Okay, the popular material is germanium and the 3,5 alloy like indium gallium arsenate, indium phosphate, and quaternary alloy मतलब indium gallium arsenate phosphate. Why these are material? Because good responsivity between 1.3, mm, because these are good because they are the 1.32 this reason. Okay, and faster carrier movement and low dark current compared to the gallium. So these devices are now widely used. Which one is gallium 3V alloys? Okay, detector for the longer wavelength, semiconductor detector. Semiconductor detector beside the main photodiode, the two additional devices under continuous heterojunction phototransistor. Okay. Conclusion. Conclusion. Conclusion of the primary devices. So what is the conclusion for the primary devices? So conclusion for the primary device. So conclusion for the most important commonly used detector today is, so most common detector used is is pin, that is pin photodiode. Okay, so because having the high speed good good sensitivity. Okay, and the and second one avalanche avalanche photodiode, that is we call it APD. Okay, because we have an internal gain high sensitivity high sensitivity than diode. Okay, used for the long distance and low power system. Used for the long distance and the low power system. Low power system. Okay, and operating wavelength region is operating region. Operating, operating wavelength region is length region is 0.8 to 0.9. Okay, 1.3 1.55. Okay, these are so, these remain the backbone of all the modern fiber optic communication. Okay, the pin diode and Nancy photodiode. So understand the device type, and so let's move forward for the another topic. What is optical detection principle? Optical detection principle. So people principles. Okay. So in optical detection in photodiode is based on converting the incident photon into the electron hole pair, which then create a measurable current and the process. Okay. So what is the optical detection principle? So, so optical this means that in in photo photodiodes, okay, is based on photodiode is based on converting the incident incident photon into the electron pair, which then create a measurable gap, which then create will then create the will then create a measurable current. So measurable current, and this process mainly occurred in this process mainly occur in the depletion region, depletion okay, depletion region of a reverse bias, mm, of a reverse reverse biased reverse biased PN junction. Okay. So optical detection in a photodiode is based on converting the incident photon into the electron hole pair, which then create a measurable amount of current, and this process occur mainly in the depletion region of the reverse or forward bias. Okay. Then so what is okay what is reverse bias PN junction? When a photodiode is reverse biased, when the photodiode in reverse bias, the electric field across the junction widen. So in reverse bias, so the electric field across the junction, across electric field across the junction widens. Okay, in the depletion region. Okay, and electrical depletion and majority carrier are prevented from the crossing the junction, and the majority carrier are prevented from crossing the junction. Okay, junction, and the minority carrier are quickly swept across the electric field and producing a small reverse leakage current. Okay, this depletion region become a intrinsic light, and the mobile carrier are removed. Second one is photo absorption and the carrier generation. Okay, a photo incident on the depletion region will. So optical detection in a photodiode is based on converting the incident photon into the electron hole pair, and then which create a measurable electric current, and this process occur mainly in the depletion region, okay, of the reverse bias. So what is reverse bias? So when a photodiode is in the reverse bias, the electric field across the junction is widened in the depletion region, okay, and minority carrier are prevented from crossing the junction, and majority carrier are prevented from crossing the junction, and the minority carrier are quickly swept across the electric field and producing a small reverse leakage current. Photon absorption and the carrier generation. When a photon energy is greater than semiconductor band gap, so in this case, what happened? Photon excite an electron from the valence band to conduction band. This leave a hole band, and together they as a electron hole pair, and this is called photogeneration. Okay. Okay. Then we move forward for the so the operation in p and diode, the photo generation of electron hole pair in the intrinsic semiconductor, and the structure of reversed bias p-n junction illustrated carrier drift. Okay, the carrier band gap of the reverse bias p-n junction showing photo generation. Okay, when our photon energy is greater than when our photon energy is greater than semiconductor band gap, then in that case the photon excite then in photon excited. Okay, photon excited from the valence band to conduction band, and the leave a hole behind, and together they create an electron hole pair something. Okay, so this one, and second reason, depletion region widened and Fermi level. Now we see what is absorption. Now we see the absorption. So, so absorption is a process by which an incident photon. Absorption is a process by which incident optical energy is converted into. Absorption is a process by which incident optical energy is converted into electron hole pair inside a semiconductor. This is the first and essential step of the absorption of the absorption of the photon in photodiode produce a carrier pair and thus a photocurrent that is dependent on the absorption coefficient delta. Okay, so what we call absorption? Absorption. So what we call absorption? So it is a process. It is a process of process by which incident optical energy photon is converted into electron hole pairs inside the conductor, and this is the first and the essential steps in the photo detection. Okay, this is the first and essential step for the what is the absorption in the photodiode. So when a photon with the energy, what is so second question is what is the absorption in the photodiode. So when photon with the energy HF is greater than Eg, that is band gap. So enter the when the photon with the when the photon when the photon with the energy of HF is greater than enter the semiconductor, then it is absorbed, and then it is absorbed. Okay, and it excite the electron, move from the it excite the electron and excite the electron and move from balance valence band to the conduction band. Okay, valence band to conduction band. Okay, and this create a leave the holes left behind, and this create a electron hole pair. Okay, this is exactly what have this is exactly that make the photo current possible. So photo current condition. Okay, okay, okay. Absorption coefficient. So first of all is what is absorption coefficient. Understand what is absorption? So it is a process by which the energy is converted into the electron hole pair inside the semiconductor. This is the first essential step for the photo detection. When the electron of energy is greater than HF by Eg, then it absorbs and excites the electron from valence band and conduction band, create a hole and leave the hole behind. So now we have absorption coefficient alpha is the one of the most important parameter defining the efficient effective. So what is this? So this is alpha. So alpha is the one of the most important parameter 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 in determining what? In determining how effectively a semiconductor how effectively a semiconductor photodiode convert incident light into the photocurrent. Okay. What is the absorption coefficient? So absorption coefficient alpha indicate how strongly a semiconductor absorb the light with a particular wavelength. Okay. So if high alpha high alpha high alpha so high alpha indicates strong absorption and many photon absorbed in the short distance. Okay. When low alpha mean a weak absorption and photon penetrate and deeper. Okay, photon penetrate deeper. So high absorption and is penetrate deeper. Since photodiode relies on photon absorption, so photon diode is relies on the photon absorption to generate directly influence sensitivity and responsivity. So photon absorption it directly influence the sensitivity and responsivity. Okay, photocurrent emission. So for the intrinsic observer, so when the optical power P naught enter the semiconductor, okay, when when optical when optical power P naught, okay, P is enter enter the semiconductor, okay, the photon current IP is produced. So this what we call, okay. When optical power P naught enter the semiconductor, the photocurrent IP is produced. So P naught E 1 minus R by HF 1 minus exponential of minus alpha D naught. Okay. P naught is the incident power. P naught is the incident power. Okay. E is the electron. Okay. And R is the Fresnel reflection coefficient. Okay. Alpha stands for the absorption. One second. Okay, let's continue. So we are discussing the absorption coefficient. So absorption coefficient is simply a parameter which defines that how effective the photodiode convert the incident light into the photokite. Okay. So whenever the alpha is high, so this indicate that if alpha is light high, so it indicates that so when alpha is high, it indicates that a strong absorption happen and many photons are absorbed in a short distance. When alpha is low, it indicates a weak absorption and photon can penetrate deeply. Okay. So and we are seeing the formula of we are seeing the optical power. When optical power enters the semiconductor, a photocurrent is produced and photocurrent formula is equal to P naught E minus 1 minus R HF 1 minus exponential of minus alpha naught D. So here P naught define the incident power electron and our Fresnel coefficient alpha is equal to absorption coefficient. D stand for the absorption region with, okay, as Planck constant F is the photon frequency. Okay, that term simply explain that if the term by understanding 1 minus R. So correct the optical reflection at a semiconductor surface level. So no need to study that much deeply. Okay, and the absorption curve for the some common semiconductor photodiode. There is the some absorption curve for semiconductor diode. Okay, in which wavelength and the optical absorption alpha. Okay, so typical absorption key material. Okay, and this one is germanium. Okay, germanium, silicon, gallium arsenide, or indium. Indium. So why different semiconductor had different absorption? Okay. The first question arises: why different semiconductor has a different absorption? Because each semiconductor has a different band gap. Okay. Because every semiconductor has a different band gap. Okay. So band gap depends the photon energy needed for the absorption. Okay. The wavelength region where the material can operate. The shape of the absorption curve, lower band gap, lower band gap, lower band gap, lower wavelength. So if gallium arsenide has the lower wavelength, okay, which is the lower wavelength, and in gallium, okay, and in gallium, gallium, okay, and higher band gap has sorry, lower band gap has higher wavelength, okay, like this one, and this one, what is the I think gallium, okay, and the higher band gap has shorter wavelength, okay. This is why different photodiode had different operation and different operation. So temperature dependence, okay. So absorption curve also change with the temperature. Band gap decreases with increasing temperature, and absorption age shift longer wavelength. Okay. Thus the alpha is not constant. Detector performance vary with the temperature and this thing. So summary of this absorption coefficient is simply alpha describes how much light our semiconductor absorbed per unit length. Okay. And photocurrent intrinsic, that formula is given as the IP is will be not E minus 1 minus R by HF 1 minus exponential minus alpha not D. Okay. So alpha strongly depend on the wavelength, metal gap, high alpha, strong absorption, high sensitivity. Alpha determine the usable wavelength region. Okay. Absorption characteristic different from the silicon with germanium, gallium arsenide, indium arsenide. Okay. Alpha vary with the temperature. Now we have to understand what is direct or indirect absorption in silicon and germanium. Okay. Now we have to understand. Now we have to understand the direct, direct and indirect absorption. Okay. Absorption. Okay. Of the silicon and germanium. So And a silica and germanium can support both, but the dominant mechanism is different from the each material in the usable wavelength. Okay, so what is the difference between the direct and indirect? Direct versus indirect. Okay, so direct absorption, the electron move from valence band to conduction and without any additional movement. Direct means the direct absorption means that an electron move from the valence band to conduction band without any momentum, without any additional momentum. Okay, momentum change. Okay, momentum change. Okay, only photon energy is needed. Only the photon energy is needed. Only photon energy needed. Okay, and high probability, strong absorption. So large, high probability and strong, large alpha. Okay, okay, and fast and efficient. Okay, whereas in the indirect absorption require both require require both both photon and phonon phonon lattice vibration to conserve the momentum plus energy, to conserve the momentum, and energy. Okay, and slower. Okay, for the photodiode, direct absorption is preferable because high sensitivity and stronger photocurrent and faster responses. Okay, and we see in the table that indirect band gap is 1.4. Indirect band gap for the silicon is 1.4, and the direct band gap is 4.4 electron corresponding. Okay, corresponding. And for the zero point 0.8 first generation, photon energy is less than band gap. Essentially, we cannot create a absorption when photon energy is less than the band gap. Okay, direct band gap, so we cannot create absorption. Only the indirect transition can occur. So these weak low absorption alpha, so these are the weak and low absorption coefficient, and above 0.19 micron the HF is less than, easy, that means indirect absorption stop. Silicon become a transparent blind. Okay, cannot detect 1.3 or 1.5 level. But germanium absorption behavior, the indirect band gap is 0.67 electron volt. You can see that the indirect band gap for the germanium is 0.67 volt. Okay, and direct band gap is 0.8. Okay, and 0.81. Okay, for the lambda less than 1.5, the photon energy is greater than 0.81, so direct transition possible and German becomes strongly absorbing. Okay, okay. This seems to have a sharp peak in the absorption curve. You can see a sharp German. Okay, and the lambda from 0.8 to 1.6, both direct and indirect absorption aluminum photon diode can use for the entire telecom band. Okay, a germanium work over all major fiber optics. Okay, choosing the band gap for photodiode. Ideally, semiconductor diode. So, ideally for semiconductor band gap should be slightly smaller than the photon energy corresponding to the longest system wavelength. Limitation of germanium height and limitation of limitation of the germanium high dark current, because germanium has a narrow band gap and it produces more thermally generated carriers room temperature, resulting in the high dark current and higher noise. The performance at short wavelength and poorer performance at the short wavelength. The germanium are good for the long wavelength, but silicon photodiode have a shorter wavelength advantage. Okay. So in short summary, we can say that silica and germanium both support direct or indirect absorption, but dominant mechanism differ with the wavelength. Okay, silicon absorb only the weakly in 0.8 to 0.9 micrometer because the absorption is indirect. Direct absorption occur at 0.3 micro absorption because absorption below 1.5 micron due to direct absorption. Indirect absorption continue until 1.8 micrometer, making the German schedule for 0.8 to 1.6 micrometer reduction. Ideal photodiode material have a direct bandgap slightly smaller than the photo energy at a longer wavelength. So germanium photodiodes suffer from the high dark current due to the narrow bandgap. Okay. Okay. Then we move forward for the quantum efficiency. Now we have to see what is quantum efficiency. So quantum efficiency denoted by eta. So uh, denoted by eta. Okay. So this is like this one. Okay. So quantum efficiency is the most important performance parameter of the photodiode or the optical detector. Indicate indicate how effectively how effectively the device how effectively the device convert the incident photon to useful electron. Okay. Okay. The definition of quantum efficiency defined energy. So it is an important parameter for the most performance parameter for the photodiode in optical detector. So it indicates how effective a device can convert the incident photon into useful electron. So it's a definition of the so quantum efficiency defined as the fraction. So quantum efficiency defined as the fraction of incident. So quantum efficiency defined as fraction of incident photon which are absorbed by the photodetector and generate electron which are collected at photodetector terminal. Okay. So quantum efficiency defined as the fraction of incident photon which are absorbed by the photodetector by the generate electron which are collected by the phototerminals. Okay. So it is a number of electron collected by the number of incident photon. So quantum fraction of incident photon which are absorbed by the photon. So which are absorbed by photodetector. So we can say that which are these are the photodetector. Okay. So the fraction of incident photon which are absorbed by the photodetector by and generate electron. Absorbed by photodetector and generate electron, and which are collected by photodetector and which are detected by photodetector terminal. Okay. Number of electrons collected, number of incident photon. So it tell what fraction of incoming photon actually generate electron hole pair to contribute the photo band. Okay. So eta defined as the RE by RP. So RP is the incident photon rate. Okay. Incident photon rate, and RE is the electron rate collected. Electron rate collected at the terminal in electron per second. Okay. These are electron per second. electron rate collected at terminal. Electron rate collected at terminal. Okay. Meaning of the quantum efficiency. So what is the meaning of quantum efficiency? If eta is equal to one, so this means 100%, 100%, and at present the incident detector. When eta is 1, that means 100% efficient detector. Okay. Every photon create one collected electron. Every photon create one collected electron. When eta is less than 1, you have partial detector. So some photons are lost and not absorbed. Okay. Some photons are lost and not absorbed. Okay. So for example, in eta is 75, when eta, so for example, when you ever say that eta is 75, so it has 75 out of 100 incident photon detector can collect 75 electrons. Okay, the remaining may be reflected, not absorbed due to the recombined or lost. So what determine the quantum efficiency? The key determining factor is the key determining factor is the absorption coefficient. Okay, of the semiconductor. So high alpha means strong absorption more EH pair, strong EH pair and beta increases. Okay. Lower alpha, this means weak absorption, fewer photon absorbed and the beta decreases. Thus the detector material must be chosen so that absorption spectrum matching this one. So silicon has a high beta and the 0.8 to 0.9 micrometer. Indium has this one silicon. Okay. And summary quantum efficiency is the ratio. Actually, summary of the quantum efficiency is the ratio of the electron collected to photon incident photon which are absorbed at the photodetector and the generate electron which are collected by detectors. Okay, terminals, and it depends on the strongly absorption coefficient. The photon material are always less than a unity due to the reflection. Quantum efficiency vary with the wavelength and thus specify the particular wavelength. Okay. What now another term is responsivity. Now discuss the responsivity. Okay. So responsivity denoted as a R. Okay, is one of the important parameter in photo which tell the how. Another is responsivity. Responsivity. Okay. So responsivity denoted by the R, and it is an important parameter. It tells us okay how much how much how much photo current okay is produced, how much photo current is produced produced for a how much photo current is produced how much photo current is produced for a given amount of incident power given produce a given amount of. Okay. So it is also an important. So it is an also important parameter for the photodiode. So it's us how much photo current is produced for a given amount of incident power. Okay, how much? So the definition of responsivity, the expression of quantum efficiency does not involve the photon energy. Okay, so as we discussed earlier, the quantum efficiency frequency does not explain how the involved photon energy. Therefore, the responsivity is often more used when characterizing the performance of photodetector. Okay, the responsivity defined as the IP by P naught. Okay, A by ampere per unit watt. Okay, IP is a photo current and P naught is incident power. Okay, responsivity tell how effectively the photodiode convert the optical power into the electrical current. Okay, okay. Now linking the responsivity with the quantum efficiency. Now we are making the relationship of responsivity with the quantum efficiency. Okay, so so photon now the quantum efficiency tell how many electron are produced per photon, and quantum efficiency simply telling the how much electron are produced per photon. So E denoted as EHF. Okay, so and the photon energy is equal to E is equal to HF. Okay, photon rate is equal to divide P naught by HF, and the electron is equal to eta by df. Okay, so electron rate defined as the as we discussed earlier. So rate of electron rate by photon rate. Okay, is called eta, and we know photon rate is equal to P naught by HF, and now electron rate is equal to this one. So we substitute the value from this one. Then the output current is equal to output current is equal to the output current is equal to simply when we multiply all with the electric. Okay, output photocurrent, and the is the electron only, and the responsivity become now responsivity is equal to I P by HF. Okay, HF. Okay, so IP is equal to eta by something. Okay, so simply write as eta by something. So now it become N P naught E by HF. P naught. So P naught by HF. So P naught by HF is simply P naught by HF. We simply add R is equal to eta Ne by HF. Okay, okay. HF. So responsivity in the term of wavelength. Now we have to convert the responsivity in the term of wavelength. So we have noted frequency is equal to C lambda. Okay, we substitute value C is equal to F lambda. So use C or lambda upon. So R is equal to N lambda by HC. Okay, so this is the most useful and widely used formula. Okay, finally the responsivity becomes eta E lambda HC. Okay, and let's see. Eta is quantum efficiency is the electron 1.6 into 10 to the power minus 19. Okay, lambda is operating wavelength, and H is equal to 6.6 into 10 to the power minus 34. Okay, and C is equal to 3 into 10 to the power minus 8. Okay, the key observation is that responsivity is directly proportional to the quantum efficiency. As we said, responsivity is directly proportional to quantum efficiency. As the quantum efficiency increases, the responsivity increases. Okay, responsivity is directly proportional to the wavelength. So longer wavelength, higher responsivity, but until the cutoff wavelength. Okay, responsivity drop at zero at the longer wavelength. Okay, so as we see, wavelength and responsivity is directly proportional. Ideal photodiode when drop after. Okay, for the larger wavelength. Okay, so wavelength silicon, drop indium, and germanium. Okay, so silicon, lambda is equal to 1, responsivity will become 0.4, okay, 0.4 approx. Offer the indium gallium arsenide offer the highest responsivity. So as we study indium gallium arsenide have a higher incident responsivity. Okay. Why responsivity drop to zero at the cutoff? For the longer wavelength. So for the longer wavelength, photon energy become less than our band gap. So no electron will be a regeneration. Okay. So we are seeing. So where we are, so we are seeing that why the responsivity drop at a zero cutoff, because as we see that after a long for a long wavelength the photon energy decreases. So photon energy is lesser than the band gap, and if this condition is satisfied, then no electron voltage generated and efficiency becomes zero. As the efficiency becomes zero, the responsivity becomes zero as by formula. So this matches the responsivity curve as a zero. So now we have to solve some numerical problem based on responsivity and